Thank you for taking the time to participate in this live broadcast. Next up is Dr. Reza for a conversation on microbiologically influenced corrosion. Hey, I'm Jim Kunkel. Welcome to a special weekend episode of Coatings Talk. Joining me this morning is Dr. Reza. Dr. Reza, welcome.
Thank you very much, James. Thank you very much, everyone, for watching this stream. And I hope that the topic we will be talking about will be of some use to the viewers.
You know, before we get into the topic about microbiologically induced corrosion, or MIC as it's called in the industry, if you could do a favor, and for those who might not know who you are, provide your professional background, and also, too, a little bit about information on why you are a subject matter expert on the subject of MIC.
Thank you. Yes, my background is in material science and metallurgical engineering. So I am particularly coming from an engineering background. I have been working as both a field engineer and an academic researcher for the last 30 years. I have focused on corrosion, and particularly microbial corrosion or microbiologically influenced corrosion. As we continue, I would try to say more words about what microbial corrosion is. I have involved in more than 400 projects worldwide with regards to identification and problem shooting of corrosion and microbial corrosion. I have authored about 10 books on this subject, published by internationally known reputable publishers such as Springer, Elsevier, etc., etc. And I have also authored more than 400 root cause analysis reports about MIC or MIC. So I can say that because I have dedicated about half of my life basically to deal with microbial corrosion, I think I am qualified enough to talk about this corrosion process. I'm not saying this kind of corrosion, this type of corrosion, because microbial corrosion is not a new kind of corrosion. It is electrochemical corrosion, and as we continue, I will try to give more details about why we cannot call MIC as a type of corrosion.
Oh, that's so true. There's a lot of misunderstanding, and there might be some watching this live stream right now who might not really fully understand what is microbiologically influenced corrosion, or MIC. Could you kind of provide, without really going into a lot of depth and detail, provide kind of an overview of what really MIC is?
Yes. Actually, if I'm not mistaken, in early 90s, then NACE called this corrosion process officially as microbiologically influenced corrosion. However, in European countries, they prefer to call it as microbiologically induced corrosion, which to me, they are both equivalent. And there are also alternative ways of naming this corrosion process. Some people call it microbial corrosion, some call it as biocorrosion, some call it as MIC, or other ways of calling. So far, I have encountered 7 ways people normally use in their research papers and talks to refer to this corrosion process. They are all okay except one that is calling this corrosion process as bacterial corrosion. This is absolutely wrong. And I will say why it is wrong. As I just mentioned, MIC or MIC is essentially electrochemical corrosion. What does it mean? It simply means that for MIC to happen, you have to have anode, the cathode, an electrolyte, and a metallic path. What does it mean? By anode, we mean a material that is susceptible or vulnerable to giving off electron. And cathode is where the electron is received. And then you will need a medium through which ions will be able to move around and travel. This is called the electrolyte. Most of the time, this is water or water containing fluids like oil or gas. And then you will also need a metallic path in order to let electrons transfer. Under realistic working conditions in industry, because corrosion does happen on metals, we normally omit this element of the metallic path because the metal itself is already there. The only difference between MIC and other variations of electrochemical corrosion is that um, in MIC you have the involvement of living organisms. You see, atmospheric corrosion or corrosion under insulation (CUI), they are also electrochemical corrosion. However, in MIC, what you have is the contribution coming from bacteria, their cousins archaea, algae, fungi, so living things. And these living organisms can contribute to corrosion in very mysterious ways. Sometimes they can accelerate corrosion. Under certain conditions, they even decelerate and slow down corrosion. So just seeing some bacteria around should not panic us. It is just a sign of warning, but it also shows that if we have done our corrosion management homework wisely and well, then just having some bacteria around may not result in alarming us for microbial corrosion. However, if microbial corrosion is indeed the case, you could expect very high corrosion rates, like losing more than 2 millimeters of the thickness of your material per year, which is quite high corrosion rate, especially if you look at the normal thickness of pipelines, for example. This means that within a very short period of time, the asset could be gone. We have documented cases that, for example, in case of flow lines, which are basically used for offshore applications, these flow lines are normally designed to have 20 plus years of design life, plus 20 years. But when you have some of these bacteria around active and contributing to corrosion, the service life could well drop down to even 3 years or low. So we are dealing with a very important issue. One thing that I want to add is that, if I'm not mistaken, every 10 days on the average, every 10 days, on the average, 16 research papers on microbial corrosion is being published. And the cost of microbial corrosion could even amount to 40% of the cost of corrosion. So for a developed country, for a developing country, the cost of corrosion is indeed very hard to afford. It could go to billions of dollars. The main problem with MIC is that most of the time it often goes unnoticed.
Mm-hmm.
You know, people think that, okay, after all, it's just bugs. We have all the necessary measures like application of chemicals that kill bacteria like biocide. We have cathodic protection. We have these. We have corrosion resistant alloys, etc., etc. So it must not be a big deal. This is exactly where the industry makes the most terrible mistake. And that's the point that I would explain when we talk about API 580 and 581.
Yeah, that's a good segue because, like you said, earlier research in the 90s going into 2000s, it was kind of determined that probably was 20% of the cost, the global cost of corrosion was due to the bacteria, the algae,
Yeah.
the fungi, and everything else related
Yeah,
to
yeah,
the
yeah.
biological. And now the studies are showing that that number is much higher. The other
Yeah.
thing that we're also finding through research is that these microorganisms can exist in very severe conditions,
That's right. Yes,
environments, being cold or hot, and
that's right.
depending on what type of application, or let's say a cargo or a commodity,
Yeah,
hydrocarbons, for example, those are a good food source for them, and for them
that's
to
right.
survive and thrive in. Water wastewater is another one that comes to mind, which is heavily, very much attacked by
That's
the
right.
biological attack. So
That's right.
let's go ahead and talk about API 580, and then also how the fundamentals in the 580 apply to MIC, and related to the oil industry.
Yeah. Actually, API 580 and 581, they are basically talking about risk-based inspection, RBI. And the central concepts in these standards, the central concept is the concept of risk. Risk is defined as a function of likelihood of a danger times the consequences associated with it. This means that the likelihood of a certain danger, like MIC, could be quite low or could seem even unlikely. But because of the consequences that it could have, either from a financial point of view or from an ecological point of view, the risk is always high. So when somebody says that we have no MIC issue in our industry, it is quite evident that this individual mixes up between likelihood and risk. And this is basically one of the main reasons that we have disasters like the one that we had some years ago in Purdo Bay, or other examples that are basically coming from this mix up between likelihood and risk. Now, API 580 says that in order to basically evaluate the likelihood of a danger, one thing that you have to know is the so-called POF, probability of failure. So without knowing probability of failure, you cannot calculate likelihood of failure. And in order to know the POF, you have to know the failure mechanism. It then follows that when we want to assess the risk of microbial corrosion, first we need to know the mechanism of MIC. And not only MIC. Let me put it this way. When we talk about corrosion, all right, we are basically talking about metals, because it is metals that can develop anode, cathode, and the so-called metallic path. But we also have microbial attack on non-metals, such as composites, such as polymers, where you don't have the so-called anode, cathode, and metallic path, obviously. And for that, I coined the term microbiologically influenced deterioration, MID, where you still have the electrolyte in which you have the ions, where they can produce the so-called electron acceptors, etc., like sulfates, nitrates, etc., that can be used as food to bacteria. Although MIC and MID both are related to the attack of these microorganisms, or sometimes macroorganisms such as algae, fungi, etc. Again, for either corrosion or deterioration, you will need the existence of an electrolyte. To cut the long story short, I could say that all engineering materials, except a few, including titanium alloys, for example, are vulnerable to microbial attack. And in order to apply risk-based inspection, RBI, correctly when applied on cases of microbial corrosion or microbial deterioration, one has to know the failure mechanism, so that he would be able to calculate POF, and from there the likelihood, and from there, of course, you could calculate risk. This is where integrity or holistic integrity management can be related to what we call as corrosion engineering.
Very good. And we have a question that came up. What is the definitive solution for controlling microbial deterioration rate on composite surfaces?
Oh, it's a very interesting question. There are ways by which this can be achieved. Actually, in composites and polymers, there are ways by which MID can be controlled. One of them, and this is just one of them, there are other measures that I have explained in details in my books. Polymers become vulnerable to microbial attack if their structure is similar to natural polymers. So the more distant the structure of the polymer is from natural polymers, such as starch, for example, the less likely it will be that it will be attacked by microbes. When it comes to composites, in composites, actually, in addition to the so-called matrix and the second phase of composites, we have a lot of materials that we put into composites, like plasticizers, glue, etc., etc. If these materials could be used as food to bacteria, then the composite itself would be highly likely to be deteriorated. We have documented cases where even epoxy and HDPE, high density PE, they have been shown to be susceptible to microbial attack.
Very good. And another question that came up for non-destructive evaluation methods to detect MIC. I know there are different test kits that can be done, but typically, what are some of the non-destructive methods to detect MIC that are available out in the market?
Yeah. Well, when we talk about non-destructive tests or NDT, we normally talk about methods such as, I don't know, radiography or dye penetrant, etc., etc. These methods cannot differentiate between MIC attack and, for example, corrosion attack by, I don't know, atmospheric corrosion
Hmm.
or by AC current. So the morphology do look like the same. That's why many post-mortem failure analyses also fail to differentiate or to understand if the failure mechanism was indeed MIC. We have guidelines basically through standards like TM0194 and other standards that can assist us in these cases. However, sorry, at the moment I am a member of an international group who is looking at some alterations, modifications, and updating the standard TM0194 because we we do need to implement a lot of new concepts and methodologies into this and similar standards as we learn more about microbial corrosion. I don't want to go through all the details, but
Yes.
yeah. But I just want to just draw your attention to a very interesting point. Before 19, if I'm not mistaken, 1982 or something. I may be wrong about the date. We were all assuming that microbial corrosion basically happens through chemical reactions. Like, for example, we have sulfur reduction in
Hmm.
case of sulfate in bacteria. We have sulfate reduction, then we have anodic reactions, etc., etc. And the same was also true for other bacteria. Since then, there is a new theory, which is in a sense a revolutionary one, that says that bacteria actually attach themselves onto the surface of the metal and actually they suck up electron directly from the metal. In this case, we now have a theory that can be referred to as external electron transfer. When we try to explain MIC just by using chemistry, the typical corrosion rates that you may see could be in the range of 16 to 20 mpy, more or less. But when it comes to the so-called EMIC, electrical microbial corrosion, the typical rates could be even 36 mpy. And according to NACE regulations, if the corrosion rates you meet are around 5 mpy, then the corrosion case is considered as extreme. So now you have something like 36. So as I said, as we continue on developing research facilities and methodologies, we start to learn more and more about MIC and MID.
So how about when you're dealing with a colony of bacteria or whatever it might be, um, testing for what form of a colony? In other words, what scientific class it is. Is that something to be important to know as well? The type of bacteria it might be, or fungi,
Oh yeah,
or
yeah. One thing which is very important is that normally we examine the so-called biofilm.
Mm-hmm.
This biofilm is a well-known term that to me is wrong, and I will explain later
Yeah.
why it is wrong. Normally, we examine biofilm, and we see what type of bacteria are present there. In addition to that, we also examine corrosion products using known chemical methods such as EDXA that analyzes elements, or XRD that examines compounds, and we put together these bits and pieces to say that okay, the case could be related to microbial corrosion. One thing is that we just don't concentrate on one aspect. Actually, when you are called upon to examine a case that could potentially be MIC related, you can actually feel yourself, literally speaking, like Hercule Poirot. It is like, finding all bits and pieces, never be satisfied fully with what you find unless you have a proof, and then you will put all these together. And like, for example, you may look at the color of the corrosion product, you may look at the smell of corrosion product, you may look at for example, at the morphology of pits, and all these need to be balanced based on the knowledge you have as an MIC expert. That's why even a normal corrosion expert could be misled by these types of evidences if he or she is not well trained in microbial corrosion.
Sure. Just to follow up here, I think you did address this one, that you're currently working with a group and an organization regarding other test methods when it comes to composites and the deterioration. And then
Yes.
This question came through about with the acceleration, deceleration of corrosion and carrying electrons. If I understand correctly, if the organism is pulling electrons out of the steel, it's basically it's breaking down that steel because it's losing its electrons.
Yes.
And then the second part of this is, how does a living organism cause non-metal corrosion if their mechanism is solely electrochemical? It's, if I understand correctly, what you're saying in this case, it's using it, potentially there could be elements in that non-metal that's being used as a food source.
Yes, this last question arises basically from the what I call of shortage of terminologies in microbial corrosion.
Mm-hmm.
We have, especially scientists and researchers, we have been accustomed to calling something as electrochemical when all the four elements that I previously mentioned
Yeah.
are present. However, when, for example, in case of MID, three of them are absent. We have no anode, no cathode, no metallic path. How come you still call it as electrochemical? I'm calling it as electrochemical because we have no other alternative terminology at the time to refer to. We cannot deny the fact that this MID has to happen when the environment does contain some ions, and these ions will make the so-called electron acceptors that later will be used as food for bacteria. Therefore, I'm not saying that it is correct to refer to MID as being electrochemical. Knowing what electrochemical corrosion or what electrochemical actually means, and knowing its limitations, we need to invent a new terminology. And one thing that I would like to add here is that, to the best of my knowledge, MID and MID mechanisms are not as well known as we know about MIC.
Yeah, makes sense. And I like this next question because, here's something that ties into the architectural industry. We're talking about the oil and gas industry. We talk about water, wastewater when we're talking about deterioration or corrosion because of microbiology. But in this question, in the case of green walls or green facades, where the soil of the plants is in direct contact with structural stainless steel, how do the bacteria act? Is it possible to simulate a soil containing bacteria for corrosion laboratory testing? That's a very interesting question. What are your thoughts on that?
Well, to be honest with you, I think this question needs to be a little bit more elaborated,
Okay.
because what we first we need to define what we mean by green wall or green facade, because if we are talking about, for example, the green layer that could cover, say, reinforced concrete, the scenario will be something that we can explain. So I would assume that we are talking about microbial attack on say something reinforced concrete, and I hope that I'm right in getting to question. If
Yeah,
this is the case,
the
if
way
this is
Yeah, the way I interpret it, and sometimes in modern buildings and airports, you will see a living wall where they have the plants, and they're
ah
irrigated down.
yeah
They're on the wall, and that
yeah
makes a lot of sense. Where they would have some aspect of a soil composition there, with
yeah
the biomaterial being the plant, and then a
yeah
water source. So there's probably a great potential. A lot of times too, and this is something we didn't really dive into, is when it's coming to microbial attack, either on composites or on structural steel or a facade like that green wall or even concrete, a lot of engineering should be done in the design phase to try to kind of mitigate or address the potential for MIC. And
yes
that's something that I think anyone watching this live stream or watching this in a replay take away is, as much as we talk about preventatives and maintenance and everything like that, there is so much that's not done in the design phase that needs to be done to take consideration for all this. And
exactly
if you can design the materials, the composites, if you can design the coating systems, uh, you could design the structure to be able to kind of deal with this up front.
yeah
You're going to be in a much better position than
that's right
when we currently are, because like you said, we're still learning, even though we've done so much research, and that average number of research papers that are coming out all the time, we're still scratching the surface of this topic. And
that's right
new theories are coming out and everything like that. We're getting better, but it's still a pervasive and ever growing problem because of
yeah
bacterias and fungi and
yeah
algae. they're
yeah
they're more resilient, and the harsher the environment, it seems like, as they always say, life will find a way. They find a way, and then what they create can also wreak havoc on our infrastructure and everything like that.
That's
So,
right. Yeah, if we know under what conditions these
mhm.
microorganisms can be prolific and active, then by cutting those lifelines, we may be sure that we have uh, controlled the potential problem largely. Like, for example, if we see these so-called green walls, etc., but somehow we could exclude extra water existing on these surfaces, then this will not allow bacteria to grow, because first thing that bacteria and other microorganisms need for their activity is having water, and this water must have a certain so-called water activity number above zero point 0.5, around 0.98. So this is something like an engineering challenge,
Yes.
that whatever we design, okay, it may look quite green, nice, a big contribution to sustainability. However, we should also try to think twice, because if in the case that I just mentioned, you have concrete structures on which you allow the so-called microbial establishments grow, at the end of the day, you would basically you would end up losing the structure, the asset, one day, sooner or
Yeah.
later.
Yeah. So now that we've gone through kind of the myths of the, applications and MIC, and then also talked about the misunderstanding or the lack of knowledge when it comes to biofilm, can we move and talk about the role of coatings in controlling and prevention of MIC? How can
Yes.
coatings prevent or control
Yeah.
MIC?
Yeah. As I said, MIC is, in a sense, an electrochemical reaction. And as we all know, there are 7 ways by which any electrochemical corrosion can be controlled or even prevented. One is by use of chemical measures, like application of inhibitors, corrosion inhibitors, and in case of microbial corrosion, biocides. Another one is by electrical measures, such as cathodic protection, anodic protection. Then is physical protection, which is by using coatings. This is 3. Number 4 is by mechanical measures, like, for example, within pipelines, you run pigs, and you do not allow um, um, corrosion products to be formed, so that under deposit corrosion will happen. The 5th measure is by design applications. You can simply change the design of the equipment, of the asset, so that it will not allow, for example, for fluid stagnation. If the fluid is water and it becomes stagnant, the likelihood of microbial corrosion goes up. There is also another way, which is not frequently seen Then there is the 6th measure, which is material selection. You have carbon steel, you change for duplex stainless steel, for example, which is most of the time quite a costly option. The 7th measure is by use of models. So far in corrosion literature, the vital role of models in prediction of corrosion, and particularly microbial corrosion, has not been taken in the way that they deserve. Getting back to your question, coatings, a research paper by NACE in 2002 showed that application of organic coatings could save about 88% of cost of corrosion, which is quite a high number. When it comes to microbial corrosion controlled by coatings, we could have 2 approaches. One is using so-called conventional coatings, that is, coatings that have so-called toxic metals, such as tin or zinc or copper in them. An example was TBT, the so-called TBT, which is not in use anymore. Another approach could be so-called environmental friendly approach. In this category, at the moment, there are three subcategories. One is is use of so-called impregnated coatings. In these coatings, you actually impregnate the coating with a biocide. Over the time, this biocide is released on a controlled way, and the bacteria that could come in contact with with the coating would be annihilated and killed because the biocide would not allow them to survive. So one approach is use of impregnated coatings. Another another approach is use of the so-called adhesion resistant coatings. In these coatings, by playing with the surface tension, you make it so low that actually the surface of the coating becomes slippery, too slippery to let the so-called biofilm be formed. Therefore, these are another category of coatings. In this category, you don't have a killing of bacteria, simply you don't allow them to be formed. The third category is what we call as coatings that use contact killing. This means that in their formulation, you use positively charged compounds. Bacteria themselves could be regarded as negatively charged particles. So, if they are absorbed on these coatings, because they will be annihilated by the opposite charge, positive charge, that there is already on the coating, then bacterial killing will happen. Mostly conductive coatings can be given as an example, and research shows that you could expect a feasibility of 97% or even more.
Wow.
And recently, about 2 3 years ago, in the Netherlands, a research was started using a very new technology that uses, in fact, nanotechnology. That you have these nano-size small balls in which you have agents that would not allow biofilm formation. These coatings are very sensitive to external factors, so that under external factors such as temperature change or stress, these little tennis balls are fractured and these chemicals are released. The inventor of this method is Dr. Assarian, and I had the honor of being a supervisor. This is something that has not been finished yet. However, I just gave this as an example
Hmm.
just to put more emphasis on the point that I made. Almost every day, in one corner of the world, you see that people are finding new ways to tackle microbial corrosion, particularly in coating industry, because it is, as I said, one of the most important industries that can assist us in dealing with microbial corrosion.
Yeah, let me bring this comment up. So I believe this is Dr. Asarian, right? Correct?
Sorry?
Is this Dr. Asarian here on the post here? Can bacteria be responsible for
Yes.
microbial corrosion? Uh, uh, be used to create surface protection films, for example, by locking them in a layer of a particular polymer or using microcapsules. I believe that's what you were just kind of going through, right?
Yeah, yeah,
Yeah.
yeah, yeah.
So,
She is the inventor of this method, and at the moment, from the laboratory research that we did, as I said, about some years ago, more than 3 years ago, we have received a very high rate of efficiency. However, we need to work more on that and bring it to more industrial level.
yeah, when you look at, for example, with the human body, we have bacteria inside of us that we have learned to become symbiotic with the bacteria and the bacteria with
Yeah.
us. It would be amazing to see research where we could actually maybe utilize bacteria, fungi, and other type of living organisms to help provide
Yes.
material protection, but maybe even do anti-corrosion as well.
Yes. Yes.
In
Yes.
certain industries and certain environments, obviously. So that is kind of a very neat approach to everything. Is
Yes. Yes.
instead of trying to destroy it, let's try to be symbiotic with it
That's right.
and use it as a tool to help
Yeah.
us
Yeah.
in that fight against
Yes.
corrosion.
Yeah. Let me borrow from you 2 points that you
Mm-hmm.
just mentioned. Actually, one of the ways by which microbial corrosion can be treated, and it has been tried on an industrial level, however, it still needs to be developed, is using bacteria against bacteria. And through methods such as biocompetitive reactions or other reactions. Basically, you use one type of bacteria against, I mean, good bacteria against bad bacteria. So this is one thing. Another thing is that I personally believe that not only for microbial corrosion, but also for corrosion in general, we do need to move forward towards natural ingredients rather than synthetic ingredients. For example, we know for years, we know that the so-called neem tree has antibacterial properties. Its leaf, its root, its fruit, and it can well be used as a biocide. We know that a mixture of honey and tobacco could lower corrosion rate as a corrosion inhibitor. The point I'm trying to make is this: if the research is rather concentrated on mimicking nature to deal with corrosion problems in general and microbial corrosion in particular, we can make sure that even if in case of a failure, what is released to the nature will not act as toxic material. It is a part of nature coming back to nature. And this is something that especially oil and gas industry does need to invest in.
Yeah, very good, very good. Dr. Reza, is there anything we did not talk about or cover that you would want to leave with the viewers of this episode?
Well, there are two things that I would like to very shortly cover, if I may. One thing is about this biofilm story. Biofilm is a term that was coined in late 70s, and it sounds like a film which is 100% biological. which is neither. It is neither a film nor 100% biological. Actually, about 60 to 70% of the fabric of a biofilm is non-biological matter. And that's why in a paper that I published about 3 years ago, I came up with a new terminology, temenos, which is a Greek name that literally means cut off. And the reason is that under biofilm conditions could well be different from conditions outside of it. You could have an anaerobic, that is oxygen-free conditions under a biofilm, where the biofilm has been formed in an oxygenated environment. So that's why I coined the term temenos instead of biofilm. The second point is that if the likelihood of MIC seems to be low, because we have application of biocides or cathodic protection or corrosion resistant alloys, etc., let's not uh, let's not mix up between the likelihood of MIC and its risk. The best remedy, the best remedy to distance ourselves from making such mistakes is training. We have to train ourselves. I don't mean just, today or tomorrow go and register for a training course, which is good actually, which is good because at least you can hear from someone who knows about what it is. But read every day and update your knowledge. You will see that certain biocides, especially I'm saying this for oil and gas people, in routine practices such as hydrostatic testing, you have the highest likelihood of microbial corrosion after hydrotest. Okay, and in order to understand that, I also want to put emphasis on this practice that most of the time our friends in oil and gas industry, particularly in gas industry, they put some oxygen scavengers materials to basically trade off oxygen, thinking that okay, by signing off oxygen, then I have no problem with corrosion. Fine, but they may not consider that by putting too much oxygen scavengers, you actually make the system anaerobic. So you will allow sulfur-reducing bacteria and other anaerobic bacteria to grow. Then there are some very well-known biocides used in oil and gas industry. When they are used together with oxygen scavengers, their biocidal effect disappears. So basically, you are wasting your money. That's why I say that tackling microbial corrosion, I'm not saying this because I have spent some of my life regarding MIC, but what I have seen is that it is such a multi-dimensional issue that one has to be very careful, think twice before applying or not applying any measures.
Very good. Dr. Reza, how can people follow you, but more importantly, how can they find your research, your books, and your other publications and other content you might have done on the topic?
Well, the best and easiest way is or will be through LinkedIn. I am very active on LinkedIn. If they just write my name, they can easily find my my LinkedIn posts and also articles almost every week, at least once, if not twice or more. I am writing some points about how MIC can be recognized, etc., etc. Another way is by sending me emails. If they just Google my name, they can easily find my contact details, and I'm always ready to be of help.
Very good, very good. And for everyone, please make sure that you like this episode. Please share this episode with your colleagues or anyone in any industry that might be tackling or looking at this particular topic. And this way you can help educate them and inform them. Also, please follow Dr. Reza and check out his content, his papers, publications. And the other important thing, too, I'd ask you to do is to also make sure that you do subscribe to the Coatings Talk channel. And just so everyone knows, Monday's live stream will be the mid-season break. And I'm going to be talking related to robotics, and they're going to be utilized in cleaning surfaces, but also too in the spray paint application side as well. So that'll be Monday evening on LinkedIn Live, but also out on YouTube and Facebook as well. Thank you, everyone. I appreciate all the comments, very good questions and everything. And Dr. Reza, it's been an honor and a pleasure to have you once again. The last time we talked on this subject, we did an audio podcast on it, and that went very well. So we should, it's good that we finally got to do it on a video. So thank you so much.
Thank you. I thank you, James, for giving me this opportunity. I also thank all our viewers, and also I hope that this has been of some help to our viewers and colleagues. Thank you.
Thank you. Okay, everyone, have a good rest of your weekend.
Thank you.